But since our audit, we're getting a bit more pressure from our state regulators on the topic of temporary controls as well as permanent controls, and that's what we're here to talk about today, the permanent controls section. So we all need to do a little bit better job of selecting those post-construction controls, and like I said, document the good things that we do. So with that, I'll present Scott. Thank you.
Thanks a lot, Jerry. Just give a quick overview of what we're going to be talking about today. Got a brief couple slides on the UDOT permit, and it's being reissued right now currently, and will probably be approved by the end of the year. Do I need to get it a little closer? Oops, yeah, if you can. So the permit, there we go. The permit's going to be approved probably by the end of the year. And we'll talk a little bit about what we have in terms of post-construction and kind of the institutional BMPs for that. And then we're going to look at 3 recent NCHRP projects that have come out that are specifically for DOTs assisting them in implementing their stormwater programs. And I think these are some really good tools that we can use to help UDOT as it goes forward to put over in its next level of stormwater implementation. So we'll be talking about long-term performance of BMPs, and then a project that was done on bridge stormwater runoff analysis. We'll talk a little bit about how bridges are different and how we should treat them a little bit differently for water quality. And then achieving volume reduction, which is specifically called out for in the UDOT permit now, to evaluate looking at infiltration, evapotranspiration, and harvest and use as really one of the first approaches that you do for post-construction. And then the way Jerry and I have structured this, we have about a half an hour, hopefully, for questions, just general discussion, Q&A at the end. All right, so we'll start out with the UDOT permit. As I said, we expect approval this year, and then really have about 180 days after that to develop the stormwater management plan. So I'm going to be covering the permit generally, and not everything's going to be cast in concrete here because there's a lot of details left to be worked out. But in general, this is what's going to be required for post-construction and good housekeeping. So the permit requires implementation of 6 minimum control measures, and that's pretty standard in EPA's world. Public education and outreach, public involvement and participation. There's an illicit discharge detection and elimination portion of the permit. And for DOTs, that really revolves around illegal dumping mostly. Not too many cross connections or illegal connections to the DOT storm drain generally, but you do get a lot of couches left in the right-of-way and things like that. Construction site runoff control, obviously everything has to be covered by the general construction permit that disturbs more than 1 acre, but there's also some oversight that the DOT has to have, particularly on third parties working within the right-of-way. We're going to focus a little bit more obviously on post-construction control, and that's permit section 4.2.5. Those are the permit sections that I have listed there. And then a little bit on the pollution prevention and good housekeeping as well. So this is the meat of it, the post-construction stormwater management portion. And the wording's kind of funny in the permit, but all improvement projects that disturb 1 or more acres are subject to this post-construction permit section. And they include this common plan of development language, which is another kind of odd way of wording it. Usually that's reserved for the construction general permit to keep people from subdividing their project up into little 0.99 acre parcels and then essentially avoiding coverage under the general construction permit that way. So this is something that UDOT's going to have to address, I think, in the swamp probably, and talk about what a common plan of development is, because the problem is with DOTs and public utilities or anything like that, your whole capital improvement project can be viewed as a common plan of development if you would want it to. But I don't think that's really the intent of the permit writer here, and it's certainly not how it's interpreted, elsewhere in the country. So that's going to have to be one that's smoothed out. The permit talks about the objective is to maintain pre-development hydrology and prevent and minimize impacts to water quality. That's pretty standard wording. I mean, maintaining pre-development hydrology really goes to the core of low-impact development, and they're trying to infuse this permit with low-impact development principles and requirements, which, again, is pretty trendy and not out of the ordinary. And that's where it talks about infiltrating, evapotranspirating, or harvesting and using runoff. Evapotranspirating runoff sounds good. In reality, when you start looking at the numbers, it doesn't go very far when you're looking at BMPs, so that's not going to be something that we're going to get a whole lot of traction out of. Infiltrating is really where it's at. Harvest and use is another tough one. I haven't seen a lot of DOTs harvesting and using runoff. You simply don't have the right-of-way to be able to do that. Could possibly do that in a maintenance facility or something like that, but the cost and the benefits really don't add up for those systems. So probably we're going to be looking mostly at infiltrate, and that's what I'm going to be spending on my time today. UDOC's on the hook to develop a sizing procedure, a treatment control or post-construction control sizing procedure. So that's a common method of sizing each of the approved post-construction controls that we're going to be using, and that's going to include some sort of a common design storm, and so that's going to have to be worked out, and that can either be a certain amount of rainfall or a certain amount of runoff. And we'll talk about, when I show you the NCHRP tools, those are all set up around the 85th percentile runoff, and that was really generated by GWO and Urbanus. They did kind of a study on that out of the Urban Drainage Flood Control District out in Denver. And I'd say, maybe a third to half of the country uses that approach when they're designing BMPs. So we can talk a little bit more about that. The permit requires a training program, so everybody has to be trained up on the permit requirements. And then there's some, again, really kind of elliptical wording on a retrofit plan. So really what regulators are interested in these days is, let's face it, the interstate highway system has been constructed, and now we're in mostly a maintenance mode. We're adding some new pieces, but in general, there's not wholesale new state and interstate routes being constructed. And so from a regulatory level, they're really interested in retrofitting the existing infrastructure that's out there and putting together some sort of plan or approach to be able to do that is what the permit is contemplating. Now, obviously, there's a lot of details that go with something like that, but that'll be something that's involved with implementing the new permit. So then the other kind of pertinent point is section 426, which is pollution prevention and good housekeeping. And this one has quite a few to-do items in it, not the least of which is putting together stormwater pollution prevention plans for all the maintenance sheds, the storage locations, and other designated facilities under this permit section. So that means having a specific runoff pollution prevention plan that is implemented and has all the things that go along with that, inspections, reporting, those types of things, as well as non-structural and perhaps treatment BMPs where those are appropriate. Also in this section, it talks about standard operating procedures for roadways and roadway operations, so everything from filling potholes to doing overlays, grind, things like that. Want to make sure that there's standard operating procedures, BMPs in place for those types of operations, all the different maintenance, what's happened, how the wastes are disposed of, storm drain system maintenance as well. cleaning, catch basin cleaning, storm drain cleaning, those types of things, an inspection schedule for those, and then some sort of a threshold established and identified for cleaning, and then what you do with, again, the disposal of those materials that come out of it. Construction site coverage. Everything has to be covered under the general construction permit, obviously, that UDOT does, but making sure that anybody that's working within UDOT's right-of-way has coverage under the general construction permit. Not necessarily enforcing the general construction permit, that's DEQ's job, but making sure that they have coverage and that they're ready to go on that stuff. And really what it comes down to anymore is notifying the DEQ if you have somebody in your right-of-way that isn't complying with the general permit. That's really your obligation. You don't want to be drugged down by a bad actor. And since you do have in your municipal or your MS4 permit the obligation to ensure that pollutants stay out of your stormwater system to the maximum extent practicable, that means that people operating with an encroachment permit within your right-of-way, you have to have some level of oversight on. And then there's interesting also section on flood management facilities and looking at, number one, potentially modifying or retrofitting flood management facilities to improve water quality, as well as when new flood management facilities are added, and this would be things like big channels, looking if there's opportunities to improve water quality there. So again, those types of details still need to be worked out. A lot of those will probably happen in UDOT's updated stormwater management plan. All right, so that's really all I had on the permit. Again, the kind of short on details right now because the permit is somewhat vague, and a lot of the specifics have to get worked out through the stormwater management plan. But that's kind of the scared straight portion of the program. You know, that's what we have to do coming up here. Now we'll spend the rest of the time talking about some of the tools that are available to help us through that. So the first one is this NCHRP. The study was called 2540, but once they're published, it gets a report number, and that's 792. And any of these are Googleable, if that's a word that can be used now. I think it is. Everybody uses that. And all of these have some spreadsheet tools in them that I'm going to be going over. So if you Google these and then go to the site, the TRB website, you can pull down these spreadsheets. And this particular project looked at the long-term performance and life cycle costs of stormwater best management practices. So we'll talk a little bit about what's in there, and I'll show you a little bit about the tools. And if there's time at the end, people want to, I've got a lot of these spreadsheets loaded up on my computer here. We could bring them up and kind of mess around with them real time. So some of the realities that came out of this study, there's a lot of data, but there's not as many data sets that are targeted specifically at DOTs, and there's not many long-term data sets. So one of the objectives of this study was looking at the long-term performance. Does performance degrade over time with a lot of these non-proprietary controls? What are the maintenance regimens that you need in order to keep them performing as they were designed? And about 5 years was the longest data set that we had in the International BMP database. Some went out to 10. But I'll just get to the punchline right away. There really wasn't a degradation of performance that we saw over the studies that had this longer term performance data. In other words, on the strips and swales and detention basins and things like that, really had about the same removal performance on day 10 or year 10 as they did in year 1. There is not good data on maintenance versus performance. And again, the study, to kind of get to the bottom line, really showed that you have a basic level of maintenance that needs to be performed, but unless the BMP just clogs or completely stops working, it generally performs as it was designed without too much of a degradation in performance. Again, there isn't a lot of empirical data there, but what we did have pointed to that result. And another takeaway is that costs are very site-specific, especially in retrofit-only scenarios. This tool was developed to really look at construction as a part of a larger project, and that's really how the pricing was set up. If you're doing a retrofit-only project where you're going out and you're just constructing an infiltration basin, the costs for that are going to be a lot higher. You have all of the overhead, traffic control, contractor laydown area, mobilization, demobilization, but you can't share that with any of the other, it's not spread across a larger project. So in this tool, it provides cost data, and I think it's actually extremely accurate. But for any given particular location, it's not going to be as accurate. And you're well advised to go in and show you the tool can be customized and do kind of your own line item bid estimate. But if you're looking at pricing out, say, 10 BMPs across a system, I would say that it's going to be extremely accurate, probably within what an engineer's estimate would be. Because this tool is set up to record, line item type estimates, bid item. So there's two levels. It's set up structural and non-structural. We'll talk about the non-structural BMPs first. Really, the whole purpose of this part of the study was to kind of look to putting together an optimized BMP program. You want to have non-structural BMPs implemented to the extent that they can, because they're usually cheaper, and in a lot of ways they can perform better than trying to strain things out at the end of the pipe. So trying to find that sweet spot where you fully implemented your non-structural or kind of your good housekeeping BMPs, and then supplement that type of a program with the structural or the treatment control BMPs, post-construction BMPs. So we wanted to look at, in this part, identifying the program variables that a DOT can manage in the non-structural BMP effectiveness to help improve the efficiency and reduce the whole life cost of the whole stormwater program. And this was done using the triple bottom line approach. You probably heard about that. It's people, planet, profit. So you're looking at, what are the social implications of something. For example, if I'm operating a municipality and street sweeping has been shown to be a very good stormwater improvement BMP, but I go out and I street sweep 3 times a week, and then I kill all the on-street parking and I'm giving everybody tickets, that's not really going to engender the public trust in my program. In fact, it's going to get a lot of people pissed off. So that's the people part of it. And for a DOT, it can be things similar to that, and it's also looking at, do you have the maintenance forces and equipment to be able to implement something effectively? And then, planet is obviously the performance side of it. Is it improving the environment? And then profit, in this case, is going to be the cost. You're looking at minimizing the cost of whatever control that you put in. So you're trying to look at non-structural controls from that triple bottom line analysis type perspective, because it's pretty difficult to determine if one's better than the other in a lot of cases, or when you've maximized it. So the BMPs that were qualitatively assessed within this triple bottom line analysis within the report are the ones you see here. Storm drain cleaning, again, required in the permit. Sweeping, same thing. Looking at irrigation runoff reduction practices. Usually DOTs don't irrigate a lot, but sometimes in certain locations they do, trying to make sure that there isn't irrigation excess. That's one of the non-stormwater discharges that you're supposed to be eliminating. Using smart landscaping, really what that just means is putting in landscaping that's consistent with the local climate, so you don't have to irrigate, and you don't have to, more importantly or equally importantly, is you don't need to use herbicides, you don't need to use pesticides or any sort of chemicals to maintain it, because that's obviously another water quality issue. Trash management programs are huge. Trash is one of the biggest issues generally for the public. It's a huge one for DOTs. So looking at your trash management program, everything from public education and outreach to sweeping to litter pickup, and then post-construction type controls would be the treatment control that goes along with that. Elimination of groundwater infiltration into your storm drain systems. It's kind of an interesting thing. Rising groundwater isn't a prohibited discharge, but if you have a storm drain system that's crossing through an aquifer that's contaminated, the DEQ starts looking at that and saying, well, you're facilitating the discharge of that groundwater into the receiving water, therefore you're touched it, you own it type of thing. So in a lot of cases we look at going in and trying to band and grout or line or somehow make a stormwater that's below the water table water, storm drain watertight. So in specific locations and situations, that's a good approach. Slope and channel stabilization is becoming pretty key. I mean, total suspended solids is really kind of a proxy for pollution in a lot of cases, and nobody wants to see a lot of sediment discharge into a receiving water, see cloudy water coming out of storm drain systems, or see a lot of sediment in general discharging onto a roadway where it can be mobilized. So making sure that you have a good program for stabilizing slopes, fixing landslides when they occur quickly is one of the key approaches for a DOT. And then lastly, winter maintenance activities, how you're putting on your traction aids and what type of traction aids you're using, things like that are extremely important. Northeast is having a lot of salt TMDLs, believe it or not, so that's impacting the DOT now in terms of salt application up there. It's a big deal, big issue. If you use sand or cinders, things like that, they tend to crush. That can then become a TSS problem and a discharge. So managing how you control traction during the winter is a big issue, and there needs to be discussion about that, usually in the stormwater management plan. So this is just a table that you can see that shows how it was presented in this report 792. And this one is an example looking at storm drain cleaning. So you can see the pollutants that are addressed. And then the second variable, or the second column there, is really kind of where you can do the important things within the DOT to maximize the benefit. So formatting's kind of crummy there, but like frequency of cleaning, timing of cleaning relative to a storm activity. If you have a very distinct dry period versus wet season, it doesn't really pay you a lot to go in, say in July, if it never rains during the summer, and clean out all the catch basins and all the storm drain systems, because it's just going to fill up again probably by September, October, when the first rain event hits. You're better off, in other words, timing those maintenance activities right before the first storm event of the season where you're expecting to get runoff. And we'll talk a little bit more about that later. The buildup wash-off on streets is kind of an interesting phenomena, and the rate that occurs. And then the type of equipment that you use for that. I mean, obviously Vector trucks are expensive, but they're really good at cleaning storm drain inlets, for example. You can get a lot more inlets cleaned with a Vector truck than you can with a crew that's using shovels, for example. So it talks about some of the institutional barriers, that whole people thing, and gives a performance range. And in this case, it's referencing a separate table. And then it talks a little bit about costs. And, a lot of times costs just are so difficult because it depends on, what type of equipment you're using and things like that. But where we had the data, we put it in there. So here you can see the effectiveness. This is that table that's referenced for storm drain cleaning. And again, it gets pretty sketchy on a lot of the data. Didn't want to start making some of this stuff up. So where we could find literature values for it, it was put in. But for example, sediment reduction, average effectiveness compared to not doing the control would be like 35% reduction coming out of the storm drain system. That ranged from 14 to 56%. And then looking at an average load reduction, if that was available again, in this case it was about 500 pounds per acre. So you can see that there's some ranges given for some other of the BMPs, bacteria, nutrients, trash, wasn't, but metals. And obviously for storm drains, bacteria is an interesting one and a difficult one. There was a really interesting study that was done, I think it was by Weston, looking at storm drain systems, and they found that if you put absolutely 100% pure, clear water into a storm drain system, when you go down to the other end and measure the outfall, you're not meeting sanitary quality standards in many cases. And that's because the storm drain provides the perfect incubator environment for bacteria. Makes sense, right? They just grow in the pipe. So they even went so far as to go through and pressure washed, a piece of the storm drain system, pressure washed the inlet, ran the water through again, and it did come out meeting standards. So everybody declared victory. But after one storm, guess what? It's back because it gets re-inoculated with bacteria from the environment. So that's why, storm drain systems are going to be difficult for us in meeting sanitary quality standards going forward. And that's why, if you can, it's good to not put in pipes, if possible, using ditches, open channels, things like that, where you do have the UV available to kill bacteria. And, we're finding it's cheaper. So that's the whole low impact development type design approach is, getting rid of the closed conduit systems and going to open and vegetated systems. So storm drain cleaning, this is just kind of continuing the theme through. We sum it up with a table here in terms of triple bottom line. You can see the effectiveness side, so that's planet, right? Bacteria low, nutrients low. Sediment, that 35%, we're calling it low, maybe-ish medium. Trash removal, medium, and that's really in inlets. If you remove the trash if it accumulates in inlets, and metals low. Cost per location, that's really, there was some DOTs had some pretty good data on, they did a lot of inlet cleaning, so we could determine how much it was costing to clean an inlet. In some locations where you have a wide shoulder, you're not doing any traffic control or much per se. It's $500 to have a crew out there, factor it up real quick, move on. If you're out in the median and you're closing traffic lanes and things like that, it gets expensive real quickly, up to that $2,100. Social and institutional packs generally low, and sustainability rating, which is just overall, on the triple bottom line, is this something that you should prioritize within your program to improve its effectiveness. And for, say, storm drain cleaning, that came in low. So not something that you would want to invest a lot of your resources in, but maybe just meet the minimum permit requirements for your storm drain cleaning and inspection, because it's not going to give you the return on investment that some of the other BMPs would. And, one of the more sustainable non-structural BMPs, for example, is street sweeping. That's something that can be done relatively cheaply per lane mile and has a relatively high direct improvement in terms of water quality and relatively low impact to the public. So you can troll through this report, take a look at that's all I'm really going to cover, just so you know how it's set up, and you can take a look at those different non-structural BMPs. But the tools are there to then optimize which non-structural BMPs you select for your program in order to increase the effectiveness while keeping the cost as low as possible. So let's talk a little bit about the treatment control operation and maintenance requirements. And that was another portion of this study. It was looking at the maintenance requirements and then looking at the cost and effectiveness. So wanted to really find out, what happens, how much do you really have to maintain BMPs? And I think everybody knows they do have to be maintained to maintain their effectiveness, but really trying to get out, how often do I have to be out there? What is the maintenance annuity for these things? And how can I establish that? So there were some DOTs that had implemented BMPs and then had done a pretty good job of tracking the maintenance requirements. And those are the ones that you see listed here. And we were able to pull these maintenance records and take a look at it. And we ended up developing kind of 3 levels of maintenance: low, medium, and high. And that was correlated then to rainfall. And the thought was that if you have more rainfall in your state relatively, you're going to have to be maintaining the BMP more, because if it's removing anything, the more volume you put through that BMP, the more stuff you're going to be removing. So in theory, the more you would have to clean the BMP. If it's not raining that much, you don't need as much maintenance. And just looking at, we had a pretty good cross-section across the U.S., looking at the different rainfalls that each of those had and the frequencies that the DOTs were maintaining them. We broke it down into these 3 kind of rainfall groupings, up to about 20 inches and then up to about 35 inches. So we had kind of these 2 markers and then 3 ranges. So below it, in between, and above 35 are low, medium, and high for maintenance. Also put in 2 other kind of distinctions: a functional maintenance, and in other words, what you need to make this whole thing work correctly and not become clogged, and then aesthetic maintenance. And that's really purely driven by the public and what the public's looking for. A lot of publics, wants a mowed shoulder, for example. It's not necessarily, a fire hazard because it's green all the time if you're up in Oregon, but the public wants a mowed shoulder. It doesn't really have to be mowed from the perspective of that shoulder functioning as a vegetated strip. So that would fall under an aesthetic maintenance category, and the cost could be apportioned accordingly. So knowing what's required from a water quality perspective versus a non-water quality perspective was something that we wanted to separate out. So this is a table that you can see here that shows the maintenance activities for a swale, and there was kind of a maintenance guide that was developed for post-construction controls and put together that DOTs can really adopt and kind of customize and make their own if they don't have one for BMPs. And you can see that for this is a vegetated swale, and if you're in the low maintenance category, and that means 20 inches of rain per year or less, you're looking at probably an annual maintenance frequency running you about 4 hours per event, and for a swale that's going to be, it talks about it in the report, but say an average of about 1,000 feet. And you're going to be looking at just having a utility truck and possibly a mower. Really what you're going to be doing most of the time in a swale is fixing anything that, if there's any scour or that's been going on, and then picking up the trash. And obviously trash pickup is probably going to occur more frequently as a part of a roadside program, but again, for minimum maintenance, this was the recommendation. And then intermittent maintenance, this can be things that are more major, where you're potentially having to kind of rebuild the swale. For example, as swales age over time, they're removing total suspended solids, and they tend to start losing their slope a little bit, and you have to go back in and regrade them and maybe replant them. So you're looking at doing that every 10 years or so. And again, fixing the vegetation or erosion, like I said. Major, that would be every 10 years. So this type of thing is provided for each of the primary BMPs that we're studying, and I'll go over what those were in just a second. So we'll get into, I'll talk a little bit about the costing, and then we'll get into the spreadsheet tool and show you what that looks like, which focuses on the cost and performance and gives you the definition of whole life cost is what it costs to design it, build it, and maintain it. And that's then looked at over essentially perpetuity. So there's a built-in cost too for reconstructing the BMP after it's reached the limit of its useful life. And that usually occurs with BMPs roughly every 80 years or so. So you're probably reconstructing, the highway about the same time that you're rebuilding the BMP. But that, when I'm talking about whole life costs, that's what I'm talking about here, is the cost to build, design, operate, maintain the BMP in perpetuity. And that's really done so that you can compare apples to apples for BMPs, because some BMPs are going to last longer, some are going to have different maintenance requirements. So when we start comparing them and looking at, how well one removes copper, for example, or whatever your constituent of concern is, you want to be able to look across each BMP and find the one that fits your site and does it for the least cost and the highest effectiveness. So this treatment control performance tool, it's physically based. It's spreadsheet, but the way it was put together, it really gives you a lot of power as the practitioner, because essentially, I won't go into the details a lot, but essentially these things were all modeled in SWIM, EPA's stormwater management model. So it's really just thousands and thousands of SWIM runs for all different rainfall type scenarios, soil type scenarios, using kind of a standard pollutant or pollutograph input. And so really what you're getting then is a continuous simulation model effectively in a spreadsheet, which is pretty powerful when you boil it all down that way. And really there's just these curves that have been embedded into the spreadsheet then that are the result of all of these SWIM models. So it really is kind of empirically based from a water quality perspective, because the performance of these BMPs has been pulled out of the International BMP database. And there's quite a few records, and we really focused on the records that were in there for DOTs, so that we had DOT functioning type BMPs in water quality. But looking at the reduction, the chemical reduction as well as the volume reduction from, if those records were available, for BMPs in the International BMP database. So again, the tool, when it looks at the performance, looks at load reduction essentially. So if you've got a vegetated swale, SWIM is actually calculating the infiltration loss in that swale based on the actual rain event that was seen at that site over many years, the different gauged rain events. So it's calculating the amount of infiltration, then it's also removing the constituents based on the performance of a swale or many swales that are in the International BMP database. And these are the treatment controls that we had developed these tools for. Swales, vegetated swales and strips, dry detention, bioretention, wet pond, slow sand filters, and then the permeable friction course overlay. And then, of course, there's hundreds of different pollutants out there, but these are the parameters. These are the generally available pollutants that were, we needed records in the International BMP database, obviously, and these are the generally available records that we had where we could give output in the tool for performance. And, it's not everything's there, but a lot of these can be proxies for other pollutants if it's not listed, and so you can approximate the removal that way. And here's just, see, I can get my phone out here and keep track of time, but these are the, got to wrap up in about 20 minutes, huh? For Q&A, yeah. So these are the post-construction BMPs that are in the tool. So you can see up in the upper left is a swale. The middle one there, middle top, is a slow sand filter. Upper right is a detention basin. And we have below that a vegetated strip, bioretention in the lower middle, and a wet pond on the lower left. On the lower right, you see is permeable friction course overlay. I think everybody's probably, I'm not sure, does UDOT use PFC?
We do use them, but we haven't often considered them to be a water quality feature.
Yeah, this is an interesting evolution. This was really something that was, discovered, if I can use that term, at the University of Texas. They were actually, for TxDOT, they were doing some sampling at the edge of pavement. And TxDOT came in and did a PFC overlay. And that's just, 2 to 3 inches of gap-graded asphalt over a conventional AC roadway. And it's a wearing course. The purpose of it generally is that protects the underlying pavement. You just mill it off every 10 years. And it's also really good for, eliminating hydroplaning, for example. The water flows in the overlay, reduces spray and improves braking. It actually is a quieter roadway surface as well. But what the University of Texas found is they had, in this picture, you can see it here. This is the PFC, and this is the conventional pavement. They had samplers right here and here. And what the University of Texas found was that you're getting performance in terms of water quality equal to a slow sand filter off of PFC. So it's really kind of like, how activated carbon works. It's just this, fractured material that has a bunch of little spaces in it, essentially. And that's really how PFC works. The particulate material gets trapped in the matrix and kind of sequestered. And you get, TSS off of, a normal UDOT roadway is probably going to be, let's call it 120 milligrams per liter. Be a good number, 100, 120. Coming off of PFC, it's 7. So it doesn't do a lot for dissolved constituents, but a lot of what you're trying to get rid of on the roadway is particulate. So it's an interesting BMP, and one that has a lot of good retrofit, so it was included in this. So here's just where the tool looks like, though. You've got a post-construction treatment control, a BMP in the middle, and it just shows that if you exceed the hydraulic capacity, the flow and SWIM was routed around it. SWIM also looked at how much was infiltrated, it was recombined, and then we looked at how much volume was left at the downstream end, and that's what comes out of the end of the spreadsheet. Where do we get the data sources? Well, the highway runoff database is maintained by the USGS. A guy named Greg Granado does a great job of keeping this thing current. It really represents kind of the, essentially monitoring data from, I think it's up to around 32 DOTs, something like that. And then we also supplemented that a little bit with the National Stormwater Quality Database, and so you can see the number of sites that are there and the number of events that are there. And then you can look at the total number of samples for each of the different constituents. So it's a very robust, influent water quality database that you're using as a part of this tool. So here's what the tool looks like, just in the project options. And the way it's set up is everything in blue is user customizable. So this is just project options. Mostly you're messing with things like the discount rate. It includes the time value of money, where you are in the country, because it obviously makes a difference in terms of maintenance and construction costs, things like that. All of that is user customizable. This is what I wanted to show you on the capital cost sheet. The costing is all done on a unit price basis in this, and you are free to go with the defaults, which in many cases are coming out of RS means. There's most DOTs have a pretty good cost database, and you're free to punch that all in here and then save it, and then the tool will use, your unit prices from your DOT, or you could just let it go with the defaults. But again, for each of them there, you can just punch in whatever unit price you want, or let the tool default to the one that's in there if you think it's fine. And then this is the output from the tool in terms of whole life cost summary. And so you can see that it gives you capital costs up at the top. Then it gives you maintenance activities, and you can go through and again specify low, medium, high, and you can specify the amount of maintenance that you want to do, and if you have aesthetic maintenance, things like that. And it also tells you how much corrective maintenance is going over the life of this BMP. And then it gives you this annualized cost, which for this one, so this is just an example I pulled off, but for this BMP, the estimated annualized whole life cycle cost for this is $4,500 a year. So that's everything, present worth or annualized cost. We present worth everything and then put it out over perpetuity. So let's run through a quick example using the tool. Here's what the first sheet looks like. And what you do is you select your region that you're in first, and then that pulls up all the rain gauges. So you can see we'd be, click right here, and it'll pull up then all the rain gauges that are in that area. And you can then specify that you're in Utah and pick the closest rain gauge to the location that you are. And I can't remember how many rain gauges we had in Utah. There was something like 350 of them that we used across the U.S. So I'd say in Utah there's probably 20-ish rain gauges that are in there, something like that. And you're free to override that if you like. So it'll bring up the closest rain gauge, but you can see in the lower blue boxes, then you can put in the rainfall depth you would like for the tool to use if you don't want to use the one that comes up with it. But it'll give you all that information. And again, we're using bioretention design, so you jump right into the next tab, and this is all tabbed across. Tabs at the bottom here, and these buttons run the same thing. But the beauty of this tool is you can specify every last detail, or you can just run it very quickly. And so if for bioretention, for example, I really only have to specify two things if I want to. And one is the volume. How big of a hole am I going to dig and fill it full of compost, right? And do I have an underdrain system? That's really it. I also have to specify the soil types around it. But in terms of designing the BMP, those are really all I have to do if I don't want to do anything else. If I want to, I can specify a whole river of things. I can talk about, where the subdrain is and how thick all of the different layers are, the porosity and permeability of all the different layers, the underlying soil infiltration. I can leave all that default, or I can specify it. And again, the default values are going to be pretty good. It's all based on the normal USGS hydrologic soil groups. And from that, it spits out then the whole life cycle costs. And then this is really the kind of the detailed table. It gives you all of the different. So this is the baseline annual average runoff volume. This is how much flow goes into the BMP. This is how much of it bypassed. So you can see in this case, 229,000. I think these are cubic feet per year come in, and 100,000 of it bypassed. 128,000 of it was captured in the BMP, and then 20,000 of it was infiltrated into the soil or evapotranspirated. And I guarantee you it wasn't much that was evapotranspirated. In fact, you can see it right here. Of the total that was captured, 128,000, 3,800 of it was evapotranspirated. So that's why I say, they always throw that in the permits, but you're talking about 2% of the water in a bioretention, which is really set up for evapotranspiration, if anything is ET. Infiltration was the bulk of it, as you can see there at 16,000. And then it proceeds to give you, the reduction in pathogens, metals, nutrients, and sediment. And we'll tab down here, hopefully. And then this is, really the benefit here in terms of the annual concentration reductions. And yeah, here's what I was looking for. It's giving you then the cost, like per pound. Let's just look at total copper. In this bioretention facility with the influent quality we had, it's 12,000 pounds or $12,000 per pound of copper removed. And if you have then like a TMDL or you have a specific constituent of concern you're targeting, you can cycle through all of the different BMPs really rapidly And then you're looking to minimize this number, right? If it physically works in your site, you can get the BMP that has the lowest whole life cost for copper reduction. You can see lead is $2,500, and then the nutrients, you're looking at $3,000 a pound for nitrate, for example. And it's a good tool too because it, it's illustrative of why we're looking at credit trading now, things like that. In a sewage treatment plant, I can probably reduce nitrate for somewhere in the area of, I don't know, $30 a pound, I'm going to say, something like that. And here I am out on the highway putting it in, and I'm spending $3,000 a pound. So, a factor of 100 kind of makes sense. They're both NPDES permits. They're both discharging into the receiving water. Maybe I ought to do my reductions where it makes the most sense. So those are some of the things that are slow in coming in our industry, but that's where we're heading. So anyway, that's a pretty quick trip through the tool. I do have to keep moving along because we got a couple of others that I'm behind. But this is really, I think, the one that you'll find the most value from. It's very user-friendly. I guarantee you'll be up and running this tool in 10 minutes. And it's very powerful. You have the power of really about 75,000 swim runs for the load reduction versus all of the entries in the International BMP database, which is going for about 10 years now, in one tool. So let's talk about bridges now a little bit. Bridges are a little bit different and something that as a designer you want to look at from a water quality perspective. The objectives of this project were to look at the water quality characteristics of bridge deck runoff and really, in essence, figure out, does it pay me to treat bridge deck runoff? The regulators are very interested in bridge decks and bridge deck runoff because it's directly transmitted into the receiving water, and everybody thinks that that somehow is worse than having it go into a storm drain and then discharge into the receiving water. And it is worse, and it's worse from the perspective of cost, and we'll talk about that. So the first thing we did under this study was take a look at, is the water quality any different coming off of a bridge deck than it is coming off of a highway? And I can bore you with a lot of nuanced discussion, but the short answer is no. It's the same runoff quality coming off of a bridge deck as it is coming off of a highway. So on a traditional roadway, what happens is that you get this buildup during dry weather, and it builds up, and there's a lot of flux in the highway environment, correct? I mean, you've got cars going by at 70 miles an hour, and it's blowing then all of this pollution into the shoulder area. Some locations you have paved shoulders. Some locations like this one, you've got maybe a vegetated swale. But the pollution coming off of this roadway is blowing into this vegetated swale, and it's really probably being largely sequestered in that vegetated swale, but when it rains, some of that's going to mobilize again and then go into the receiving water. But bridges are different. You can see that anything that builds up on this bridge is going to have the same dynamics, right? You still have that same energy flux. So as the car goes by, creates the big vortex, the pollution blows off, but where does it blow to? Directly into the receiving water. If it's not raining, which is what you're going to get if the pollution's blowing off the bridge deck, then that pollution in essence is lost from the system. So we started thinking about that dynamic on a bridge. Really, what is it that you're treating from bridge deck runoff? Is there really a benefit to doing that, and how much of the pollutant load am I going to be able to capture on kind of an average annual basis if I go to all the trouble to treat the bridge deck runoff? So the first answer to that question is really to look at constituent buildup. What is this buildup wash-off thing? If I go out and start with a completely clean roadway, how long does it take for that roadway to get dirty, quote unquote? And so this is a really interesting thing. This was done actually back in '72 by Boyd. Some of you guys may know Boyd. He also was the guy that worked on SWIM, and he's now, I think, at Colorado State. But they did this thing where they essentially went and they completely cleaned a road in urban areas with different land uses, and then they just measured how long it took for the pollution to build back up to pre-cleaning levels. And that's what all these curves are. And you can see in residential and commercial, the curve flattens out after like 2.5, 3 days. So if you start with a completely clean roadway, in about 3 days, it's back to dirty again. And the other interesting thing is that these curves do just flatten off. So where is the rest of the roadway pollution going? Well, it turns out that the gutter and the street surface itself just only have so much capacity to hold dirt. And then when it gets beyond that and starts stacking up, the flux of the passing cars is pushing that off over into the shoulder. So that's interesting. You think, so if I'm in a bridge environment and I have low or no railing walls, and railing walls do make a difference, essentially the bridge deck is going to be nearly always clean, right? So about 83, so we did this dry wet loading analysis and just looking at various portions of the country, and we purposely focused on wet areas. How much of the pollutant load is being deposited on the bridge deck during dry periods? And what we found out, again, looking at these very wet areas, the Pacific Northwest and actually the Northeast, where they have many, many wet days per year, like 120 or so. But using this graph combined with the inter-event periods for these very wet areas, we still found that about 83% of the pollutant loading occurs during the right-of-way during dry weather. So in a bridge condition, then, you're going to be missing out on essentially 83% of the pollutant loading because it's being blown off the bridge deck. And you'll be able to capture about 17% of it, would be, quote, then treatable with BMPs from the bridge. So that was one of the takeaways of this study is, on the efficacy side, does it make sense to spend a lot of money putting BMPs on a bridge deck? And really, I'll get to the end point here. No, I mean, it makes a lot more sense to treat a piece of conventional highway from an efficiency standpoint than to treat a bridge deck, because most of the pollution is blowing off the deck, and you're not going to be able to ever capture it in your BMP. But what are some of the other factors that affect water quality for a bridge? And again, it's looking at some of maybe those non-structural approaches. It's the configuration, materials, operation, and maintenance. The other thing we found is that not only is treatment of deck runoff inefficient, right? You're only getting that 17%, but it's expensive because you have to put in a deck drain system and pipe it back to the abutment and build something at the abutment to treat the runoff. Very expensive to do. So the cost is high and the effectiveness is low. But there are things you can do. I mean, one of the things that we found was that bird roosting and nesting can contribute to water quality issues. There's a study, this one also done in Austin, Texas, where the swallows come, they have the problem with the bats on the Congress Avenue Bridge, but they have a lot of swallows that nest there. And they measured water quality upstream and downstream of a bridge during swallow nesting season, and then there was an appreciable difference in the sanitary quality in the receiving water. So one of the things you can do is eliminate the locations where the swallows like to nest, and that's at the acute angles in the superstructure. They want to build their nest right here. So you come in and you put something like this, or hang something down like this. It still leaves this, so I wasn't so sure how good that would be. Or the little spiky things, or some sort of a curved piece in there would probably be more effective. But eliminating in your bridge superstructure design the opportunity for nesting sites. Other things that you can take a look at are the materials, what you're putting on your bridge deck. PCC has been found to be somewhat less polluting than AC, because you don't have the petroleum products essentially in the matrix. Galvanized steel is a big source of zinc. I've seen studies looking at runoff right below a bridge deck railing where you're getting zinc in thousands of micrograms per liter. So Having exposed zinc surfaces that aren't painted is tough. Paint is a big issue because it has to be constantly maintained. Looking at what you're doing for traction control, sweeping is actually one of the best things you can do on a bridge. And then some DOTs have been looking at scupper plugs, where they actually plug the scuppers in the bridge during the non-rainy seasons and sweep, and then remove those right before a rain. I think that's dicey from an operations perspective. If your crew doesn't quite make it out there before the rain event, you can roll your own dice, I guess. So the overall conclusion from this study, we did a lot of essentially runs looking at various combinations of bridge sizes and receiving water sizes, trying to look for that super big bridge deck crossing a very small stream, for example. And we ran water quality models looking at what the difference upstream and downstream of the bridge. And I'll tell you, the bottom line is you can't see the difference from a bridge deck in a receiving water quality. There's just, this is, for those of you that went to the school in the 70s and the 80s in the environmental engineering program, dilution was the solution to pollution. That's exactly the answer here. You cannot see the difference upstream and downstream of a bridge in runoff water quality because the deck is simply too small and the concentrations of pollutants are simply too small. So the contribution is de minimis. But when you're in an urban area, does that argument make sense? Not really, because if I exempt this facility and this parking lot and say, can I see, the contribution of this in the receiving water? Of course not, no. But what it does mean is in rural areas of the state where you've got a bridge, even crossing a high value water, it's not causing or contributing to the violation of a receiving water standard. It's not. I mean, we conclusively kind of showed that. So really then you're left with special consideration for urban areas, threatened endangered species present, TMDL watershed, outstanding national resource waters. Again, you're not contributing there, but it comes down to perception. It comes down to what's written in your 401 permit. So you have to comply with that. But from a technical perspective, it's not an issue. So if you're in a rural watershed, we give you tools to demonstrate that the impact is de minimis, and you can show that very easily with pretty simple models that we put together for dilution. In urban watersheds, like I say, all bets are off. You really have to look at the cumulative impacts, and the de minimis argument is kind of gone. So what you're left with then is the MS4 permit requirements. Essentially, you've got, if you're putting in a new bridge and it's over an acre, you've got to do something. But the potential, and then where this is driving and the value here, is to look at, can I treat an equivalent amount of roadway, terrestrial roadway, instead of the bridge deck? And that's going to do two things. It's going to be more efficient, and it's going to cost you a lot less, because you're not going to have to put in a very expensive scupper system to collect the water and pipe it to the abutment. So in the rural areas, put on your applicable source controls. Don't leave an exposed zinc bridge. Try to eliminate the nesting areas and roosting areas for birds. Look at how you do your traction aids in the winter. For urban areas, look at this off-site, off-project, maybe just at the approach slab treatment rather than treatment on the bridge deck. And to help you with that, we put this deck drain system cost tool in. And it's just a very quick thing that you can look at and specify. You just specify the deck area and your rainfall intensity and the type of bridge you have. You can see this box girder design. And this thing will essentially price out your deck drain system. So you can go and you have some tools to show the regulator, look, I've got this report here that says that I'm only going to be 15% effective in treating pollution from this bridge deck. And look, it's going to cost me an extra $100,000 to put this deck drain collection system in. Can I take this money and treat my terrestrial source that's untreated right now, roadway section, be a steward of the public funds, and get a lot more performance for the environment? I can even do it on a roadway that discharges upstream into the same water body. So there's not an issue with that. So here's just a quick, look at the tool. You can see you just have these slider bars, put in the bridge length, the deck width, the longitudinal slope, and the cross slope and things like that, and it'll come up with a deck drain system. It also allows you to play around with the shoulder width, because that's one of the things that we've done on some bridge decks when we're just backed into a corner, is we offset the drainage inlet off from the railing wall a foot or so, and that way the water quality flow can bypass the inlets and go off to the abutment and be treated. But then the drainage flow, once you start getting the spread out into the travel lane, well, before it gets to the travel lane, you're picking it up in the drain and keeping your dry lane criteria. But that's a kind of a cheaper way then to get the water quality flow off the deck. Cheaper in that maybe not, because per square foot of bridge deck is running you $200, right? So you're putting in additional shoulder width that way. All right, this is the last one that we wanted to talk about, which is good because I'm way out of time. And this is volume reduction approaches for highways. And this is, again, required in the UDOT permit. And I think it's something that will be a useful tool going forward. This is 802, searchable. So it looks at the efficiency of this pollutant removal compared to other treatment controls. Highly efficient, really, because you're essentially infiltrating the whole water quality volume. But there's some other issues that you want to be aware of that we'll talk about quickly here. It's an effective element in a treatment train. A lot of times you want to do some pre-treatment, and like I say, it's required to be assessed in the UDOT permit. This project report called it a volume reduction approach, a VRA, and that's just keeping with the time-honored thing in stormwater where you got to have another acronym so you can talk in code. So here's the organization, kind of a stepwise approach for incorporating volume reduction, how to use the manual, volume reduction in the urban environment, what are the approaches, the post-construction controls that you can use, and then selecting and applying these approaches. And then there's a whole slew of appendices, got some BMP fact sheets essentially, and some really useful checklists that you can go to kind of size up a location. But really, this report helps you decide if it's something that you want to do. Can you do it? I think that the highway environment is a very difficult place to do infiltration. Particularly, a lot of times you're on a fill prism, you're at 95% relative compaction. It's not a friendly place to do infiltration. You're probably better off in cut sections doing it, where you're just cutting through native. But this helps you kind of sift through the questions of should you do it, how much should you do it, and maybe if you do it, should you do it carefully? And these are things that you want to look at too. Where's the groundwater? Is the groundwater contaminated? Am I going to be pushing more water into a contaminated groundwater area that then's going to be popping out somewhere else, for example? And looking at your volume reduction approach too, am I going to be able to infiltrate fast enough so that it's ready to take the next storm event? Am I going to have to make this thing so giant and it's going to take so long to drain that the vector control agency is going to be down on me and it's still going to be half full when I get the next rain event? So it helps you kind of look through and make some of those decisions. And again, those are kind of continuous simulation modeling problems. And the tool that we have for that helps you with that. So chapter 3.4 helps you through the site conditions. What are factors of safety? These are all things that UDOT's going to be putting in its guidance manual. Minimum infiltration that you want to have, how you do the on-site testing, what's the factor of safety that you apply to your infiltration rate that you have so that the thing doesn't clog prematurely. All valid questions and all things that you need to look at. Do I want to jam too much water in the ground? Am I going to start having problems somewhere else with a rising groundwater table? The permit's right. You don't want to go beyond what the natural hydrologic balance is and change that too much, because there's unintended consequences, and you find those out after you've built, but usually before the 10 years of construction defect is up. So there's some practical tools that UDOT can use in here: checklist, worksheet for site assessment, suitability screening, feasibility screening, and helping you prioritize which volume reduction approach is the best. And then there's the tool. And the tool is really a version of the tool that I already showed you on 792, so we don't have to slog through a lot of this. But essentially, it's a bunch of swim runs that looked at the ET, infiltration, essentially the volume reduction. Looks the same as the other one that we did. You just specify your rain gauge, all user customizable, put in your tributary area and the amount of imperviousness in your tributary area, and then it'll calculate all of the flow parameters and the runoff coefficient. It'll calculate all the flow parameters for you, and it will then, here you have the, this one that I picked here was just for dispersion. So if you've got sheet flow coming off of your roadway, how much volume loss am I going to get by dispersing the flow over a given area within my right-of-way? So I have my dispersion footprint, the underlying soil infiltration rate, and if I'm even have the option to amend the soil depth to a certain, to improve, you know, the dispersion or the infiltration of the water. And then it just kicks out these very report-friendly figures. You can just snip these and put them into your report that you put into a regulator. Gives you how much volume is running off of your drainage area, how much you're infiltrating, so the percentage captured and the percentage bypassed. And you can just play with the size of your area or putting in, you know, enhancing the soil with compost and tilling the upper 6 inches or whatever to get to whatever volume reduction you need. Here's some, you know, just a picture that shows a typical kind of good place where you could do something like that. This picture, you know, there's a pre-treatment sediment basin, and then it goes into an infiltration basin. So these types of interchange areas are typically good for highway infiltration. You really want to keep your depth low because that keeps your unit loading low, which keeps your solids loading low, which keeps your potential to clog low. Here's another one. Just this was a swale that was put in. Kind of cuts through here. You can't see it, but inlet and outlet of the storm drain, and then the swale through here, all enhanced. And it's just essentially a rock gallery, kind of an infiltration trench, and we're able to get to the volume reduction goal that we wanted there. So there's just some of the example forms and checklists that you can go through to help you assess the site suitability and if it's the good way to go for the BMP. All right, so I went longer than I told Jerry I would. Sorry, Jerry, but we still do have 15 minutes and love to talk about it.
Thank you. For questions, I'm going to run the mic back to you guys because it's really super hard to hear what the question is. So, and then I'm going to run it to you, Glenn, and then I'll run it back for Scott's response. So otherwise, you really can't hear what's going on.
Thank you, Jerry. We're starting to use snouts a little more often. I didn't see much discussion on that today, the oil skimming snout that, have you heard of those? Before it goes into a, we're going to put it into a snout at the final box before it goes into a manhole that ties into a creek.
Okay, thanks, Glenn.
Yeah, those types of, the snout is really good for floating debris. So it's a good way to exclude trash, floating trash. You know, for oil and grease in highway runoff is just not an issue. You're looking at 5 milligrams per liter or less of free oil and grease in highway runoff. The only places where we do anything for trying to remove free oil and grease would be at a maintenance facility, and that's a maintenance facility that's just dirty. You know, we put them in and tested a few at dirty oil and grease facilities. We put in an oil water separator, a coalescing plate separator, and they fill up with dirt. You know, there's just not enough free oil and grease, but those types of things are good for trash. They may not be the best because they're not a positive screen. So you might want to look at those in terms of maybe some other non-proprietary trash device that would have better efficiency and the same maintenance cost.
We're being told by the people in Salt Lake, the water quality people, that we need to prove, show documentation on all of our projects that we are implementing some sort of BMP for water quality. And I know the best is vegetation, but in those times when it's just a trunk line along the side of the road and then going into a creek, what's the best thing we can do? We were going to say, when in doubt, snout it out, but now I'm doubting the snout.
Yeah, that's a tough one. Generally putting in, anything like that has to be maintained individually is tough, because you're going to end up with those things all over the state then, and you're going to have to keep track of them, you're going to have to deal with them. The best thing are the passive, if at all possible, if you can put in passive treatment devices. So that's going to be vegetated strip, vegetated swale. For areas where you're like right up against a sound wall, highly urban area, we're going to be, I think UDOT's going to address that in its swamp and its guidance manual. There's a technical feasibility kind of checklist that you need to go through. And for areas where you don't have the space and it's not feasible, you may be able to get to the point where you don't treat that water just because of the infeasibility, and you maybe end up treating something somewhere else or treating more on another project. I mean, that's something that hopefully will be feasible in the future. If you're backed into a corner, some sort of an into-pipe solution is probably the way to go. In that case, then, something that's easily accessible, like a net at the end of the storm drain or something like that, visual. I can go down there, I can just peek over, look, is the net full? Takes 5 minutes to change the net, something like that. I don't know, each case is different, but I personally tend to shy away from drain inlet solutions just because they're difficult to maintain and they're costly to maintain.
Thanks, Scott. One of the tricky parts in us all moving forward is documenting this process that Scott described today, which amounts to documenting what did you arrive at as your solution for water quality for this particular project, and then how did you arrive at that? When they came and audited us a couple of years ago, they asked exactly that. Well, what do you guys do for post-construction controls? And I talked about it in general terms, but I couldn't get specific because we don't really do a great job at documenting how we come up with our control measures, and then where are they all? Well, they're all over the state. We don't do a great job at that either. So that's going to be our challenge from Central, is to help the regions deal with documenting the good things that we do. And we do a lot of good stuff. So we probably have time for maybe one more quick comment if somebody wants to give us one final parting comment. Okay, Rod.
So what recommendations do you have for UDOT, which is all of us, from a program? How do we implement the program, which includes management, operation, construction? That's not a short answer, by the way, obviously, but that's our struggle. It's how do we go from the permit down and get everybody involved with that?
Good question, really challenging question too. Well, part of that I think will be answered in our improved processes moving forward. I mean, Baker's going to do a lot to help with that and to give us more tools, more opportunities to learn how to design these features, and then we're just going to have to learn how to document these better when we get the questions asked, I'm sure that EPA is not done with us yet. They're going to continue to watch how we do things going forward. And I think that's going to go a long way to answering the next time they come to Utah to look at what we do. What do you guys do? And so now we're going to be better equipped to show them the good things that we do. Like I've said, we do a lot of great things. It's just hard to manage it all and hard to bring it all together in a package to show them, well, this is what we did on these projects. So yeah, we're doing better than we did. So, and that's kind of why we hired Baker, because of their national expertise in dealing with stormwater throughout the country. They can help us on this path to success, I think. So.
Yeah. And I'd just add, it's going to be your stormwater management plan. That's going to be the top level document that specifies all these programs. And then you're going to have tools below that. You're going to have a guidance manual for post-construction controls. You're going to have a maintenance manual for post-construction controls. You're going to have a database to know where all those post-construction controls are. You're going to have stormwater pollution prevention plans at every maintenance and storage facility. Those guys are going to be doing inspections and reports at all those, and all that stuff is going to be rolled up into an annual report. So it's really like Jerry says, a lot of it's going to be more formalized documentation than you've had before. Because I was out at your maintenance sheds, and those things were clean. They do a good job out there, but nobody's writing it down and doing all that stuff right now. So I don't think it's going to be as nearly a big a culture shift for UDOT as it is for some other DOTs. Trust me, I really don't.
Oh boy, we got one late comment here from Mr. Russell.
Scott, I was just thinking we worked on some Caltrans with you, and it seemed like just if we do make more interstates down the road and more main highways and stuff, when we were looking in California specifically to look at places where we can implement BMPs and vegetation and whatnot, it seems like we have curb and gutter, we have barrier for safety from a roadway standpoint, but then it forces a storm drain system with inlets, pipes, single point discharges like Glenn was talking about. But it seems like we're now looking at it a different way. It's almost like, let's get rid of the curb where we can, let's get rid of the barrier where we can, as long as it's safe for the driver, so that we can dissipate and have this system that's, whether it be the UV rays getting or whether the overall area and making the depth lower. It just seems like you almost go that way with the systems now. It's almost like a 180 almost.
Yeah, that's exactly right. I mean, we're trying to get rid of guardrail and curb. Absolutely. Disperse water, have it go off into a vegetated shoulder. Absolutely. You can't do it in a lot of cases where, the grades are prohibiting it and you're in a big cut or a big fill, obviously. But you're trying to minimize that stuff. Before, that was the standard procedure, right? Have a rolled curb and that was it. Now, no, it's dispersion if possible. And it's cheaper to construct. We're finding that too, where we can. But, it's not everywhere all the time.
Actually, we have like 5 more minutes left. So.
I just wanted to follow up on that comment. Looking at barrier scuppers, that's something we've used in the past, but we may not have used it in its full potential. Where barrier scuppers in the past have maybe been a 4-inch diameter hole spaced every 50 feet. We need to look at mimicking the natural flow patterns better and possibly lengthening and spacing the scuppers closer. But it's just looking at processes we do currently and looking at ways to improve that.
It's a good comment. We had kind of an issue on a recent project where we called for this great new barrier scupper that was about 3 feet in length, 4 inches in height, but that didn't get communicated to the construction folks on the construction side and then our inspector side. So what we ended up with was something less effective than that. We ended up with these 4-inch diameter holes every, like Jeff said, like every 50 feet. Communication is really critical with everything that we do at UDOT, and that's just one little example of where we could communicate better. it's a challenge, and we realize that, so we're trying to do that better. Any other questions? Yes, Chuck.
Thanks. Scott, you mentioned about a third of the states you've studied are going with that 85th percentile runoff event as your target. Is that the direction that Utah and UDOT in particular are going? And if not, what are the other choices and what would be the advantages of those choices to UDOT and Utah?
We're thinking about that. I noticed that in DEQ's draft MS4 permit, they gave an idea to use the 2-year 24-hour storm event that would be a whole lot more water than the 85th, but we're still thinking about that actually, on what to use.
Yeah, I can't answer your question because it hasn't gotten there yet, but I can give you the.
Okay.
Oh, okay.
I can give you the latest anyway. A couple of weeks ago, I met with DEQ. We convinced them to get away from the 2-year 24-hour storm event. They're looking at possibly doing the 90th percentile storm. A little bit bigger than the 85th. That's a possibility. We're still trying to convince them that the best thing to do is compare it to pre-development hydrology, allowing for variances in soils, slopes, different things, and making it site-specific. The EPA is putting pressure to make it numeric, so that's why they're leaning towards a number, but they are open to that discussion. It still remains to be seen where they will end up.
Thanks, Paul. Any other comments? Well, great. I want to thank Scott and Baker for helping us out with this project and this presentation today. You did a great job. Appreciate it. Let's give them a hand, guys.
Thank you, sir.